Hi everyone, my name is Félicie and I am a scientist. I work at the Livermore National Lab, and today, because I'm working from home these days, like many of us, I'm going to share a little bit of my work and what I do with you. I do a lot of experiments using lasers. So you've probably all heard about lasers, right? It's something that's used in a lot of places in our daily lives. They're used at the cash register to scan for grocery prices. They're used to read CDs. They're used for eye surgery. They're used to cut through metals. So lasers are a really unique and powerful tool. And actually, it stands for light amplification by stimulated emission of radiation. And the L of laser stands for light. So why not do a lot of cool experiments that use light? So a laser, if you've seen one, and you've probably seen one, this is a laser pointer right here. A laser pointer, if I take a piece of paper, okay, I'm gonna get closer here, and then I shine the laser onto the piece of paper, you're gonna see a little red dot, okay? And if I get my hand further away, or the laser further away from the piece of paper, what you can see is that it just stays a little dot, right? And if I was to shine this laser super far away in my backyard, well, it would just still be a tiny dot. Now, if I do that with regular white light, like this one, this is a convenient pen. It has both white light and a laser. Well, you can just see that the blob of white light is going to get bigger, bigger, and bigger, and bigger until it disappears because it's not very intense. So, if you see a light bulb, you can see that it emits light that's either white or yellow. And wherever you put yourself to look at that white bulb, you're still going to see the light. A laser, on the other hand, is only one color and produces light that's possibly very intense because it has the ability to put the light in one direction. So at the Livermore Lab, we have small lasers, but we also have very big ones. And in fact, we have the biggest laser in the world. It's called the National Ignition Facility. It's about the size of 3 football fields, and we use it to do a lot of experiments. Among them, we're trying to achieve fusion. For our experiment today, I want you to grab a piece of white paper, like this one, a pitcher that you can fill with water, and an empty glass. Any size and shape will work. And I want you to grab a pen so that you can draw on a piece of paper. Let's try to draw something on a piece of paper. Let's say an arrow. Okay. Not a very good artist, but I'll try my best. All right. Show me your best arrow. Perfect. Now let's take our empty glass and just pass it through. You can see that nothing really happens. You can still see your arrow, just roughly looks the same colors and same size, more or less. Okay, now let's take our pitcher and fill the glass with water. And if I take this and I put the glass in front of the arrow, you can see what happens. All right, I do here and here. Yeah, this is not magic, this is physics, and we can explain this from a cool property of light that is called refraction. So let me go back to my home office and explain refraction with a little bit of graphics. So refraction is a property of light, and it can explain what we've just seen with our glass of water and our arrow. Normally, when you have a ray of light, it propagates into a medium, for example, the laser beam that I showed you earlier, or rays of sunshine propagate in air. And when they propagate like this, they propagate into a straight line. However, when your ray of light encounters another medium, like water, part of the light is going to be reflected, and then part of the light is going to propagate into water, but it's not going to propagate in the same direction. It's going to slightly change its direction. It's going to be refracted. This is what refraction is all about. It's when a ray of light crosses another surface and as a result, slightly changes direction. So in the case of air and water, it's a specific example, but each medium has what we call an index of refraction. We call that N. So let's go back to our example of air and water. Air has an index of refraction of 1, and water has an index of refraction of about 1.3. And so it's going to dictate the ability of water to bend the propagation of a ray of light. And that property applies to any material. If we take another material, say glass, it also has an index of refraction, and it's slightly higher than the index of refraction of water. So what it does is that it slightly bends a ray of light more than water would. If we take our example with the glass of water, well, this is really what happens. So I've showed you a nice arrow that I have drawn on the piece of paper. And so if you were to take rays of light that depart from the arrow, they just propagate straight in air, and then they encounter the glass of water that I put in front of the arrow. So what happens in this case is that the rays of light, they are going to be refracted. So they're going to be bent, and they're going to be bent like this. If they're bent enough, so if you have enough water, then each ray is going to cross. And then when they reach the other side of the glass, they'll go from water to air. So they'll go from a medium that has a high index of refraction to another medium that has a low index of refraction. So they're going to be bent the other way compared to what we've seen earlier. That's what's going to explain why the rays that you were seeing at the beginning are flipped by passing through that glass of water. And so if you're an observer placed at the end of your glass of water, it's going to make it look like your arrow is pointing backwards. All right, everybody, that's a wrap. That's it for the experiments. I hope you had as much fun doing it as I did. And I thought I could finish this video by telling you a little bit about how I got to become a scientist. So I was born and raised in France. That's where I grew up, and that's where I got all of my education. And then I came to work at the Livermore lab only after my PhD. So when I was little, I remember that I had a lot of curiosity. I liked to ask questions to my parents. I liked to read books, to look at the stars using a telescope. And I think I remember that when I was a kid, I either wanted to be an astronaut or an orthopedic surgeon. So I am not doing either of these jobs, but at the time I surely didn't know what lasers were and that you could make a living working with lasers. And so I decided to study physics in college, and at some point I was offered the opportunity to go do an internship at the University of Central Florida in Orlando. So I thought this was really cool for two reasons. The first one is that I was going to learn to speak English, because I didn't at the time, or not very well. And the second thing was UCF is close to Cape Canaveral, and I will be able to see a space shuttle launch. So off I went. I stayed there for 2 years. I saw a space shuttle launch. And one of my professors there offered me an internship where my job was to build a laser. And I got hooked. I immediately loved this. I loved building lasers. I loved tweaking optics. And that's when I decided that I wanted to become a laser scientist and use lasers for my job. So I came back to France. I did my PhD in physics using lasers. And after that, the professor who had offered me that internship at UCF called me when I was about to graduate and said, "Hey, I moved to a place called Lawrence Livermore Lab. How about you come and try to work in my group and see if you like it?" This was 12 years ago. I still haven't left the lab. I have enjoyed my career there since. And so I think this tells one thing is when you're in high school or when you're studying, you probably don't know exactly what it's going to be like in your job, but you will meet people, you will be given opportunities. And so my advice would be to try to keep your eyes open. And sometimes things don't go according to plan, and that's fine, but be open to new opportunities. I never knew I would be a laser scientist. I never knew I would work with lasers, but I'm enjoying it very much now. If there was one thing that I could tell to my high school self, I would say sometimes it's okay to fail, if you have bad grades or if you're not happy with something that you've done in school, that's okay. And this is the case also in my job. Every mistake or failure is an opportunity to learn something new or something differently. And it's not because one day you have a bad grade in math or physics that you're not made for that. And also, something I wish I knew when I was in high school is don't necessarily listen to what other people think. What's important is that you follow what you want to do. And so if somebody tells you, oh, are you sure science is really for you? Well, don't listen. If you like science or if you like something else, just go for it and give it your best. So with that, I still have one more thing I want to share with you, and then we can say goodbye.
All right, because I can't do outside biking, I'm going to do indoor biking, and this is actually pretty cool. I'm sure that a scientist is behind this wonderful invention that allows you to put your bike on a machine and pedal like if you were outside. So that's what I've been doing. And with that, I'll go on my ride and I'll say goodbye. And I hope you all stay healthy and you stay safe and take care of yourself. And then we'll get all together through this. But in the meantime, don't forget to do some good science and learn about some cool science. All right, bye everybody.